Welcome to the Sleep Porch. Tonight, we drift into the wonders of the cosmos, a place so vast our minds can't even begin to comprehend it. Out there, far beyond our solar system, the universe is full of immense activity. For billions of years, entire worlds have been created and destroyed in a potentially infinite cosmic cycle. Astronomy offers a glimpse into this miraculous world, where stars collide with unimaginable power. Planets drift through the endless darkness, and invisible forces warp the very fabric of reality. There are ancient galaxies that defy explanation, colossal black holes that seem to break the laws of physics, and countless wonders still waiting to be discovered. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, take a slow breath. Let your body soften and allow your mind to relax. Let's begin. Stars can explode with enough power to outshine entire galaxies. When a massive star reaches the end of its life, its core can no longer support its own weight, and gravity suddenly wins. The core collapses inward at incredible speed, crushing matter into a state more compact than anything we can experience on Earth. In a fraction of a second, this collapse rebounds and sends a shockwave racing outward through the star's outer layers. Enormous amounts of energy flood into space in the form of light, heat, and ghostly particles that pass through almost everything. For a short time, that single dying object can blaze brighter than the combined starlight of billions of suns. The blast tears the star apart, flinging enriched material into the surrounding space. That debris carries newly forged elements, which will eventually become part of other stars, planets, and perhaps living beings that look back and study the long-faded flash. Planets sometimes drift freely through space with no star to warn them. These solitary worlds are thought to be born in planetary systems much like our own. Early in a system's history, young planets jostle and tug on one another as they circle their central star. If the dance becomes chaotic enough, one of them can be flung outward with such speed that it escapes entirely. Once cast loose, it travels through the darkness between stellar neighborhoods, illuminated only faintly by distant suns. Without steady light from a nearby star, its surface may freeze solid, forming a crust of permanent night. Deep inside, though, leftover heat from formation and the slow decay of radioactive elements can keep its interior warm for billions of years. Some researchers even imagine thick atmospheres or buried oceans on such bodies, hiding whatever chemistry unfolds in that hidden warmth as the planet wanders silently through the void. Black holes can spin so rapidly that they drag the very fabric of space around them. When a massive object collapses to form one of these extreme remnants, it can preserve not only its mass, but also its rotation. If that rotation is fast enough, the region around the black hole becomes a whirlpool of warped space-time. Anything nearby, from gas clouds to passing particles, feels this twisting. Space itself is forced to rotate, pulling matter into a spiraling motion that no engine could recreate. Close to the black hole, there is a zone where nothing can remain still relative to the distant universe. Even light must swirl around, caught in the rotating geometry. This region, called the odosphere, allows energy to be extracted from the spin, feeding powerful jets and high-energy emissions. In this way, the rotation of an invisible, compact object can influence its entire cosmic neighborhood, shaping the growth and behavior of its host galaxy over long ages. Beneath layers of ancient ice, certain moons hide oceans deeper than any found on Earth. In our own planetary system, several small bodies orbiting giant planets show cracked frozen surfaces marked with ridges and streaks. These patterns hint at something moving underneath. Measurements of their magnetic and gravitational fields suggest vast reservoirs of liquid water concealed below shells of ice that can be tens of kilometers thick. In these dark oceans, there is no sunlight to drive familiar forms of life. Yet, energy can come from another source. As the moon orbits its parent planet, changing gravitational poles flex its interior, generating heat through constant stretching and squeezing. That warmth can keep water from freezing solid even far from the sun. On the rocky seafloor, hot vents may pour mineral-rich fluid into the surrounding water, creating environments where complex chemistry can thrive. These hidden oceans remind us that habitable environments might be common in places that from the outside look cold and lifeless. Galaxies can race toward one another at unbelievable speeds. Gravity does not only pull on nearby objects. On the scale of clusters and superclusters, entire swarms of galaxies move under each other's collective attraction. Over time, this motion can bring two enormous star systems together on a slow but unavoidable collision course. Though their individual stars are spaced so widely that direct impacts are rare, their mutual pull distorts each galaxy's shape. Great streams of stars and gas can be drawn out into arcs and tails that stretch for hundreds of thousands of light-years. As their clouds of gas pass through one another, they can compress and ignite bursts of new star formation, transforming the appearance of both systems. Eventually, after a complicated gravitational dance lasting hundreds of millions of years, the two galaxies can merge into a single, larger structure. What began as separate swirling islands of stars becomes one more massive and often more rounded cosmic city. Some stars cool so dramatically that they begin to resemble giant planets. Not every object that forms from collapsing gas becomes hot enough in its core to sustain the same kind of nuclear reactions that power ordinary suns. Some fall short of that threshold and settle into a twilight category. They can start out relatively warm and bright, then slowly release their heat into space, fading and cooling over billions of years. As their temperatures drop, their visible light weakens and their emission shifts into the infrared. Their atmospheres can contain clouds of metal-rich grains, droplets, and exotic molecules that do not survive in true stellar furnaces. At certain stages, their spectra and colors become strikingly similar to those of enormous gas worlds. Yet these objects are not planets either, because they formed on their own from collapsing clouds rather than in orbit around a larger star. They occupy a space between familiar categories, showing that nature's creations do not always fit neatly into simple labels. Comets often carry organic molecules that formed long before the sun existed. These icy visitors are thought to be leftovers from the vast cloud of gas and dust that collapsed to build our planetary system. Within that original cloud, tiny solid grains served as surfaces where atoms could stick together and react in extremely cold conditions. Over time, simple substances like carbon monoxide and methane were transformed into more complex compounds that include chains of carbon, hydrogen, oxygen, and nitrogen. When clumps of ice and dust assembled into comet nuclei, they locked in this ancient chemistry. As a comet nears a star, its frozen surface warms and releases gas and dust into a surrounding coma and tail. By studying the light from these outflows, scientists have identified a range of organic materials, including some that resemble building blocks used by living cells. These findings suggest that the ingredients for biology can form in deep space long before any particular planet emerges from the swirling material. Nebula can glow fiercely when newborn stars flood them with intense radiation. In certain regions, clouds of hydrogen and other gases are dense enough to spawn a new generation of stellar objects. As the most massive of these young stars ignite, they emit torrent sets of energetic ultraviolet light. That radiation streams into the surrounding cloud and strips electrons from hydrogen atoms, creating large volumes of ionized gas. When electrons later recombine with protons, they release photons at specific wavelengths, producing rich colors that can be seen through telescopes. The resulting luminous region can span many light years, with intricate shapes formed by the interplay of gas density, stellar winds, and gravity. Dark lanes of dust may snake through the glowing material, casting sharp silhouettes against the bright backdrop. Over time, the combined influence of radiation and outflows from the embedded stars can erode the original cloud, carving bubbles and cavities and eventually dispersing much of the gas into space. Extreme gravitational forces can stretch planets into elongated, egg-like shapes. This distortion happens when a world orbits very close to a massive companion, so that the pull on its near side is significantly stronger than on its far side. The difference in attraction creates tides not only in any oceans, but in the rock itself. Over long periods, these tidal forces can reshape the planet's overall figure, drawing material toward the line that connects it with the object it orbits. Instead of a nearly spherical form, such a planet may bulge noticeably, with its longest dimension pointing toward its star. The constant flexing of its interior generates heat, altering its geology and potentially driving intense volcanic or tectonic activity. Its atmosphere, if present, can also respond to this unusual geometry with strong winds and complex circulation patterns. Observations of these distorted worlds give astronomers a natural laboratory for studying gravity's influence on solid matter under conditions that cannot be replicated on or near Earth. Pulsars emit perfectly timed beams of radiation that sweep the sky like cosmic lighthouses. These objects are the rapidly spinning remnants of massive stars that ended their lives in catastrophic explosions. What remains is an incredibly compact core, with a diameter comparable to a city, but containing more mass than the Sun. This core spins with astonishing speed, sometimes rotating many times each second, and it possesses a powerful magnetic field. Charged particles trapped near the magnetic poles are accelerated to high energies and emit focused beams of radio waves or higher energy radiation. As the object rotates, these beams sweep through space, and if one passes across our position, we detect a pulse of emission. The intervals between pulses can be stable to a remarkable degree, rivaling the precision of atomic clocks. Astronomers use these regular signals to test theories of gravity, probe the distribution of matter in our galaxy, and even explore the subtle ripples in spacetime produced by distant pairs of orbiting remnants. Gas giant planets can brew storms larger than Earth that refuse to fade. Inside the colossal atmospheres of these worlds, towering layers of gas move and churn under the influence of deep internal heat and rapid rotation. The clouds are made of substances that would be exotic on Earth, including ammonia, methane, and even crystals of more complex compounds that condense under extreme pressures. These layers slide past one another at different speeds, creating shear zones where turbulence grows and begins to organize itself into immense atmospheric gas. Some of these rotating systems gather more and more momentum over time, pulling in vast amounts of energy from the planet's interior. Because there is no solid surface to disrupt them, they can persist for centuries. Their colors, shapes, and behaviors shift slowly as the surrounding bands feed them or drain them. Each storm becomes its own dynamic environment, with lightning, temperature gradients, and towing cloud tops that rise high above the surrounding atmosphere. These long-lived tempests show how profoundly different weather can be on worlds where the rules of motion and heat play out across scales that dwarf our entire planet. Entire galaxies sometimes form with so few stars that they appear almost empty. Astronomers have discovered faint systems in which only a scattering of stars glows against the vast darkness of space. These ghostly galaxies may have begun as ordinary concentrations of gas, but various influences can stifle their ability to create stars. Interactions with larger neighbors can strip away the raw material needed for new stellar births, leaving only thin remnants behind. In other cases, early generations of stars may have blown out much of the available gas with powerful winds, preventing later waves of formation. What remains is a structure dominated by dark matter, holding a fragile sprinkling of stars in place. Through long observation and careful analysis, researchers can trace how these sparse systems still follow the gravitational rules that govern richer galaxies. Their dimness helps reveal the hidden architecture of cosmic evolution, showing how environments, collisions, and ancient events can shape a galaxy's destiny long before its stars grow plentiful. Even the faintest of these stellar gatherings carries the history of forces that acted over billions of years. A stellar remnant can shrink to the size of Earth while becoming incredibly dense. When certain stars exhaust their nuclear fuel, their outer layers drift away into space, leaving behind a compact core that no longer generates fusion. Without the outward push of nuclear reactions, gravity squeezes the remaining material into a volume similar to that of our own planet. However, the mass stored inside this small sphere can be comparable to that of the Sun. Under these extraordinary pressures, atoms are forced into arrangements that cannot exist in ordinary conditions. Electrons behave collectively, creating a form of matter that supports itself through quantum mechanical principles rather than thermal pressure. These remnants cool slowly over immense stretches of time, releasing their stored heat into space. Their faint glow and unique spectral signatures allow astronomers to study the transition between active stars and the final states that await many of them. They also offer glimpses into the behavior of matter under conditions that challenge the limits of physics, revealing insights that laboratories cannot match. Planetary systems occasionally develop with planets orbiting at impossible-looking angles. As newborn systems emerge from swirling clouds of gas and dust, they begin with disks that appear orderly and flat. Over time, gravitational influences from nearby stars, passing objects, or giant planets within the system can tilt or twist the orbits of smaller worlds. These interactions may be gentle or extremely violent depending on the masses involved and the timing of the encounters. Once the geometry begins to shift, resonances can amplify the misalignments, sending planets onto paths that rise far above or drop far below the plane in which their neighbors travel. Observations of exoplanetary systems have revealed worlds circling their stars along dramatic inclinations that defy old expectations about planetary formation. Studying these unusual configurations helps scientists understand the diversity of cosmic environments and shows how fragile the earliest stages of planetary development can be. Each tilted orbit offers clues about long, finished events that reshaped the system in ways that are only now becoming visible. Metal-rich asteroids can hold more precious material than Earth's crust. Scattered across the solar system are fragments of ancient bodies that once experienced intense heating, melting, and differentiation. In some of these early worlds, heavy elements like iron and nickel sank toward the center, forming dense metallic cores. Long ago, collisions shattered some of these differentiated objects, sending pieces drifting through space. When we detect these fragments today, we find asteroids composed of nearly solid metal buried beneath thin layers of dust or silicate rock. Their interiors can contain concentrations of valuable elements far higher than anything found naturally on our planet's surface. By studying their spectra and densities, scientists learn not only about future resource potential, but also about the violent history of planetary formation. These metal-rich remnants preserve the internal structure of primordial worlds, offering a direct window into the processes that shaped the earliest solid bodies, long before planets settled into stable orbits and oceans of molten rock cooled into crusts. Massive stars burn through their fuel so quickly that their lives end in an instant compared with cosmic time. Although these colossal stars possess far more hydrogen and helium than ordinary suns, they consume their supplies at astonishing rates. Their cores burn fiercely, generating staggering amounts of energy that stream outward as intense light and heat. This powerful radiation pushes outward so strongly that the stars must balance their own brilliance against the inward pull of gravity. The more massive the star, the more violent this struggle becomes. Over relatively short spans, the intense pressure forces the core to fuse heavier and heavier elements, pushing the star toward an inevitable collapse. While a smaller star may shine for billions of years, these giants blaze through their existence in spans that on cosmic scales are closer to moments. When they reach the end, their deaths unfold in spectacular ways that reshape surrounding space. The heavy elements forged in their cores spread outward, enriching the environments where future generations of stars and planets will form. Some planets reflect so much starlight that they shine like tiny suns. Their bright appearance comes from highly reflective cloud decks or surfaces composed of materials that scatter incoming radiation with remarkable efficiency. These worlds may orbit close to their stars, receiving intense illumination that bathes their atmospheres or terrains in continuous brightness. The chemical composition of their clouds or ice layers shapes the way light bounces from them, creating a brilliance that can rival much larger objects. Some of these reflective worlds have temperatures so high that minerals vaporize into fine particles, forming shimmering layers that intensify their glow. Astronomers studying these planets can detect their reflected light even when the planets cannot be seen directly, revealing details about their atmospheres and orbits. Their luminous appearance helps researchers explore how different temperatures, pressures, and chemical mixtures influence a planet's ability to reflect radiation. Certain regions of space contain magnetic fields millions of times stronger than Earth's. These powerful fields emerge near compact remnants, dense clusters, or environments where charged particles move through concentrated gravitational landscapes. When material spirals inward toward a collapsed object, it can generate electric currents that intensify surrounding magnetism. The result is an invisible structure that guides particles along tight paths, accelerating them to extraordinary energies. These strong magnetic zones shape the behavior of gas, dust, and radiation, influencing everything from the formation of jets to the emission of intense bursts of light. In some cases, the fields become so dominant that they deform atoms, stretching them into unusual shapes not found in familiar conditions. By studying the light from these environments, astronomers can trace how magnetic forces affect matter under pressures and temperatures that cannot be reproduced on Earth. These findings deepen our understanding of the physics that govern some of the most extreme regions of the universe. Galaxy clusters can bend and stretch distant starlight into graceful, luminous arcs. The immense mass within these clusters creates gravitational fields strong enough to distort the paths of photons traveling through them. As light from remote galaxies passes near these concentrations, space itself curves, guiding the rays into new trajectories.
When the alignment is just right, the distant galaxy can appear warped or magnified, forming arcs, rings, or multiple images. These distortions reveal the distribution of both visible and unseen matter within the cluster. Observing these patterns allows researchers to map hidden structures composed of material that emits no light of its own. The faint, stretched shapes provide a natural cosmic lens that can amplify objects too distant to study directly. Each distorted image carries clues about the expansion of the universe, the growth of structures, and the mysterious components that shape the cosmic web. Dying stars sometimes release gas in complex shapes that look sculpted by hand. As these stars exhaust their fuel, their outer layers loosen and drift away. Gentle pulses of energy lift shells of gas outward, while faster winds follow, catching and reshaping the earlier material. The resulting structures can form rings, hourglass shapes, or delicate filaments that twist through space in intricate patterns. The colors arise from different elements glowing in response to the star's fading heat. Over time, the central remnant cools and dims, while the expanding gas spreads into the surrounding environment. Each structure reflects the star's internal rhythms, rotation, and magnetic influences during its last active phases. These beautiful shapes reveal the dramatic transformations that occur when stars reach the ends of their lives, returning their enriched material to the galaxy. Star-forming clouds can collapse under their own gravity to create entire families of new suns. Across the galaxy, immense reservoirs of gas and dust drift in near darkness until some disturbance unsettles their quiet. A passing shockwave, the pull of a nearby cluster, or the lingering influence of an older generation of stars can send subtle ripples through the cloud. Once any region becomes dense enough, gravity takes hold and begins drawing the material inward. As the collapse accelerates, the cloud fractures into multiple pockets, each one growing hotter and denser at its center. Within these hidden cores, pressure builds until the gas begins to glow with the soft, rising warmth of a forming protostar. Surrounding each glowing center, gas settles into swirling disks that shape the flow of matter and set the stage for worlds yet to come. Over time, an entire group of newborn suns emerges from the same collapsing structure. Some are massive, some are small, and many may become companions orbiting together. These families of stars carry a shared origin. Their early histories, written in their motions and compositions long after the original cloud has vanished. Planetary orbits can evolve into strange, elongated shapes after gravitational encounters. When planets share a system with massive neighbors, their paths around the star can be influenced by interactions that unfold over long stretches of time. A close passage between two worlds may nudge one of them outward, increasing the eccentricity of its orbit until it resembles a stretched ellipse instead of a near circle. Additional tugs from other bodies can exaggerate the effect, turning a once stable path into something far more extreme.
These elongated orbits carry planets close to their stars during one part of the cycle and far into colder regions during another. Such variation can reshape climates, atmospheric chemistry, and geological processes. Even minor encounters can accumulate, gradually shifting orbits into configurations that defy initial expectations. Observations of distant systems reveal worlds moving in ways that suggest long histories of gravitational shaping. Each distorted orbit tells a story of past interactions, hidden events, and the invisible architecture of forces that sculpt the evolution of entire planetary families. Black hole jets can shoot particles across distances larger than their host galaxies. Near the centers of certain galaxies, swirling disks of superheated material spiral toward a compact object with a gravitational pull so intense that nothing crossing its inner boundary can escape. Before material reaches that final point, magnetic forces and rapid rotation can channel a portion of it upward and downward along tightly focused axes. These channels become the launch sites for streams of charged particles accelerated to speeds close to that of light. Once unleashed, the jets pierce through surrounding gas and continue outward for vast distances. Some extend far beyond the structure of the galaxy itself, carving narrow paths through intergalactic space. Along the way, they illuminate clouds, ignite shock fronts, and heat clusters of material that might otherwise remain cold. Their presence reveals the power hidden within compact remnants and shows how these objects influence environments far larger than themselves. The jets serve as beacons, tracing the flow of energy from regions where gravity dominates all other forces. Some moons experience tidal heating, strong enough to melt rock deep underground. As these moons travel around their parent planets, they often follow slightly oval orbits that carry them closer during part of the cycle and farther away during another. The changing distance causes shifts in gravitational pull that stretch and compress the moon repeatedly. This continual flexing generates friction within the interior, warming layers of rock and ice that would otherwise remain frozen. Over time, that warmth can accumulate until pockets of material melt, forming reservoirs of liquid far beneath the surface. In some cases, the heat drives plumes that erupt through cracks, sending vapor and particles into space. In others, it fuels slow circulation within subsurface oceans that remain hidden under thick crusts of ice. These internal processes reshape landscapes from within and can create environments where complex chemical reactions flourish. Despite extreme cold on the surface, the heat produced by tides demonstrates how the motion of a moon through gravitational fields can transform its interior far beyond what sunlight alone could achieve. Ancient starlight can travel across the cosmos for billions of years before reaching Earth. When a distant star or galaxy emits light, that light begins a journey through the expanding fabric of the universe. Along the way, it passes through regions filled with clusters, filaments, and voids that can stretch or shift its color. Some wavelengths are absorbed by gas clouds, while others continue uninterrupted until they reach our telescopes. Because the universe is vast and constantly expanding, the distance the photons travel is immense. By the time they arrive, the sources that emitted them may have changed dramatically, or even ceased to exist. The light becomes a record of how those objects looked eons ago, frozen in time and preserved within its wavelength and intensity. Scientists use these ancient signals to reconstruct the early eras of cosmic evolution and to see structures as they appeared when the universe was young. Each photon carries information about its birthplace, creating a timeline of events that would otherwise remain forever hidden. Dust-filled nebula can hide fully formed stars behind thick veils of shadow. Within certain regions of space,
clouds of fine particles gather so densely that they block visible light from passing through. These dark nebula appear as silhouettes against brighter backgrounds, masking whatever lies inside. Though the dust obscures the view, infrared observations reveal that many of these regions contain stars already glowing with heat. The dust grains absorb and scatter visible wavelengths, but longer wavelengths slip through more easily, allowing astronomers to peer into the concealed interiors. Inside these collapsing pockets, newborn stars gather material from the surrounding gas, forming swirling disks that may eventually give rise to planets. The same dust that hides their early glow also plays a crucial role. It cools the cloud just enough for collapse to continue. As the young stars strengthen, their light and heat slowly push the surrounding fog apart, revealing clusters that spent millions of years growing in secrecy. This interplay between darkness and hidden light makes these nebulae essential laboratories for understanding how stars evolve from infancy to visibility. Meanwhile, violent stellar winds can strip atmospheres away from vulnerable planets. When massive or highly active stars release streams of charged particles at immense speed, these winds sweep outward, flooding nearby space with energy. A planet orbiting close to such a star may find its upper atmosphere battered by this continuous onslaught. Over time, the particles can collide with atoms in the atmosphere, heating them and giving them enough energy to escape into space. Planets without strong magnetic fields are particularly at risk because they lack the protective shield that can deflect or channel the incoming wind. As the atmosphere thins, the planet's surface becomes more exposed to radiation and extreme temperature swings. In some cases, such erosion may transform a once temperate world into a barren landscape. By studying the interactions between stellar winds and planetary atmospheres, scientists can evaluate which worlds may remain stable and which face long-term depletion. These insights shape the search for environments that might support life. High-energy radiation from massive stars can sculpt nearby clouds into towering pillars. When young giants ignite within a dense region of gas and dust, they release intense ultraviolet light that sweeps outward in all directions. This radiation ionizes the surrounding material, pushing against it and driving shock fronts that reshape the cloud. Less dense areas evaporate quickly, while regions with slightly higher density resist erosion. Over time, these resistant clumps become elongated structures. As the surrounding gas is stripped away, they form tall columns and ridges that point back toward the energetic sources that sculpted them. Within the protected interiors of these pillars, gravity can continue to act, forming new stars shielded from the harsh radiation. Observations of these structures reveal dynamic environments where creation and destruction unfold simultaneously. The pillars stand as monuments to the power of massive stars and the resilience of the material from which future generations of stars may emerge. Magnetic fields in space can twist and confine blazing streams of charged particles. Across galaxies, charged particles move through environments shaped by invisible magnetic structures. These fields arise from the motion of conductive gas, the rotation of stars, and the dynamics of compact remnants. When particles encounter these fields, their paths bend, spiraling around the magnetic lines instead of traveling straight. In regions with strong fields, the particles can be trapped and guided along narrow channels, forming streams that glow across multiple wavelengths. These confined flows may appear in jets, arcs, or loops that trace cosmic activity in fine detail.
By examining the shapes and intensities of these structures, astronomers can infer the strength and orientation of the underlying fields. The behavior of these trapped particles reveals how magnetic forces influence energy distribution, star formation, and the evolution of cosmic structures. These interactions provide insight into processes that remain difficult to replicate in terrestrial laboratories. Planetary collisions can reshape entire worlds in a single catastrophic moment. During the chaotic early stages of a system's formation, countless solid bodies move along intersecting paths. When two sizable objects meet at high speed, the resulting impact can alter their structures in dramatic ways. Mountains can melt, oceans can vaporize, and crusts can be shattered. Some collisions merge the bodies into a single, larger world, while others tear them apart, scattering fragments across the system. These fragments may later reassemble into moons, rings, or smaller companion bodies. The heat generated by such impacts can create global magma oceans that reset a planet's surface entirely. Evidence of ancient collisions is preserved in cratered landscapes, unusual rotations, and unexpected compositions. By studying these scars, researchers reconstruct the violent histories that shape the planets we see today. Each collision leaves an imprint that reveals how even stable-looking worlds are the products of intense and transformative events. Rings around distant planets can stretch wider than the distance between Earth and the Moon. These enormous structures form when material becomes trapped in orbit around a planet rather than merging into a single moon. Dust, ice, and fragments of rock circle in countless individual paths, each grain responding to gravity and tiny collisions with its neighbors. The brightness and texture of a ring system depend on the size and composition of its particles. Some rings shine softly with fine icy grains that scatter starlight, while others contain darker fragments that absorb more light and appear faint even when they span incredible distances. In young systems, collisions between forming moons can produce fresh debris that spreads into broad arcs. Over time, gravitational interactions carve the rings into narrow bands, gaps, and waves, creating patterns that shift gradually as the orbits evolve. When astronomers observe rings around distant worlds, they see more than beautiful structures. They see evidence of ancient impacts, migrating moons, and the subtle forces that shape entire planetary systems. These vast rings show how dynamic and varied worlds can be, even when they lie far from the warmth of their stars. Some stars orbit each other so closely that they share outer layers of gas. In these extraordinary binary systems, two stars form so near each other that their gravitational fields overlap. As they evolve, one may expand into a swollen giant whose outer layers spill over toward its companion. The flowing material forms a bridge between the two bodies, creating a swirling region where gas circulates under the tug of both stars. This exchange can dramatically alter their fates. In such systems, the receiving star gains mass, growing hotter and brighter, while the losing star becomes stripped down, exposing inner layers that would otherwise remain forever hidden. Within their shared envelope of gas, complex patterns of heat and motion emerge, currents that can spark eruptions, generate flares, or send rhythmic pulses of radiation sweeping through space. Observing these entwined stars gives astronomers a rare window into stellar evolution, because each star reshapes the other's fate in ways that solitary stars could never experience. Their shared life stories reveal how cosmic companionship can produce outcomes far more dramatic and far more intricate than either star could achieve on its own.
Dense globular clusters can pack hundreds of thousands of stars into tightly bound spheres. These ancient collections orbit the outskirts of galaxies like glittering beacons of stellar history. Each cluster contains stars that formed at nearly the same time, making them some of the oldest surviving structures in the universe. Because they are so densely packed, the stars within them lie far closer together than the stars in typical regions of a galaxy. In such crowded conditions, gravitational encounters are frequent. These encounters can fling stars outward, draw others inward, and alter orbits in ways that create a constantly shifting internal environment. Some of the stars found in globular clusters are unusually blue and bright because they are thought to have formed through mergers or mass transfer events triggered by those close interactions. The clusters maintain their tight shapes because their combined mass keeps the stars bound together despite the constant motion. Studying them reveals how early star formation unfolded and how nature preserves these ancient spheres across cosmic time. The interstellar medium can carry shockwaves from ancient supernova explosions. When a star explodes, the blast sends out a powerful front of energy and material that sweeps through surrounding space. Although the interstellar medium appears thin, it contains gas, dust, and charged particles that can be pushed and compressed by these waves. As the shock travels onward, it heats the material it encounters, sometimes triggering new chemical reactions or exciting atoms to glow in characteristic colors. These waves can continue expanding for millions of years, shaping the structure of nearby clouds and influencing the birth of new stars. The effects ripple outward across immense distances, leaving behind shells, bubbles, and filaments that mark the path of the ancient explosion. By examining these patterns, astronomers can estimate when the original supernovae occurred and how much energy it released. Each shockwave becomes a messenger from a long, vanished star, carrying information across space in the subtle changes it imprints on the interstellar medium. Some planets orbit so rapidly that their years last only a few Earth days. These worlds circle their stars at such close range that gravity pulls them along dizzying paths. With each swift orbit, they experience intense radiation and dramatic temperature swings. Their surfaces or atmospheres face challenges no planet in our solar system encounters. On the star-facing side, heat can build to levels that melt rock or vaporize minerals. On the far side, temperatures can plunge sharply unless powerful winds distribute heat efficiently. The quick pace of each orbit creates unique atmospheric patterns as currents struggle to keep up with the rapid cycle of day and night. Some of these parrots are locked so that one side always faces the star, intensifying the contrast between scorching light and deep darkness. By studying these extreme environments, scientists learn how planets respond to conditions far beyond those on Earth. Their short years and blistering climates expand our understanding of what worlds can become. Spiral galaxies can grow new arms as they interact with neighboring systems. The graceful spirals that define these galaxies may appear stable, yet their shapes are influenced by gravitational forces from surrounding objects. When another galaxy passes nearby, even without direct contact, its pull can disturb the distribution of stars and gas in the spiral. Waves of density can propagate through the disk, compressing material into arcs that gradually curve into new arms. These arms are not rigid structures, but patterns where stars bunch together for a time before drifting onward. Gas within the arms becomes denser, encouraging the formation of bright young stars that enhance the spiral appearance. Over millions of years, repeated interactions can reshape the entire structure of the galaxy. In some cases, new arms emerge, while older ones fade or twist into distorted loops. Observations of such transformations reveal how galaxies evolve through encounters, and how the cosmic environment influences their long-term development. Massive star clusters can light up the surrounding gas with intense ultraviolet radiation. Clusters containing many hot young stars produce significant amounts of high-energy light that streams outward in all directions. When this radiation meets nearby clouds of hydrogen-rich gas, it strips electrons from the atoms and heats the cloud. The gas then glows with a distinctive set of colors that reveal its composition and temperature. The surrounding region becomes a bright nebula with tendrils and shapes carved out by the forces at play. Winds from the stars push the gas outward, while the radiation sculpts pillars, ridges, and cavities. Over time, as the cluster evolves, the brightest stars burn out quickly, leaving behind a changing landscape of light and shadow. These illuminated regions help astronomers trace how star formation progresses within clusters, and how young stellar communities influence their environments. The brilliance of these regions showcases the power that even a single cluster can exert on the cosmic neighborhood around it. Rogue stars can travel at immense speeds through intergalactic space. These solitary travelers are believed to have been hurled out of their home galaxies by powerful gravitational encounters that sent them speeding into the darkness. Some may have swung too close to a supermassive black hole, while others were ejected during turbulent interactions among clusters of massive stars. Once displaced, they race through the cosmos with no galaxy to anchor them, drifting through regions where starlight is sparse and matter grows thin, making them incredibly difficult to detect. Yet their astonishing speeds and lonely trajectories hold clues to the violent events that launched them. By tracing their motion backward through space, astronomers can reconstruct the cosmic upheavals that set them adrift. And though these stars wander alone, they still carry the chemical fingerprints of their birthplaces, preserving quiet stories about the galaxies they once called home. Their journeys remind us that even stars can experience dramatic displacements that send them wandering across the great emptiness between galaxies. Some planetary systems form multiple asteroid belts that resemble cosmic rings. During the early stages of formation, leftover material from the birth of planets can remain in stable orbits around a star. These belts consist of countless rocky fragments, ranging from tiny grains to substantial bodies. Over time, gravitational influences from planets sculpt the belts into separated regions, rather than continuous fields of debris. The gaps between the belts form where resonances disrupt the orbits, clearing paths that remain empty. Each belt reflects the history of its system, showing how collisions, migrations, and gravitational shaping have distributed the debris. The presence of multiple belts suggests a complex past, with interactions that influenced how planets settled into their current positions. Observing these structures in distant systems allows astronomers to compare them with familiar features, like the asteroid belt and the Kuiper region of our solar system. These comparisons deepen our understanding of how planetary systems evolve and how debris patterns reflect their early history. Quasars can shine with the power of trillions of stars combined. These extraordinary objects reside in the hops of young and active galaxies, where vast amounts of gas spiral towards supermassive black holes. As the material falls inward, it forms a disk that heats to extreme temperatures from friction and compression. The disk radiates across the electromagnetic spectrum, producing enormous luminosity that outshines the entire galaxy.
Surrounding clouds absorb and remit the radiation, creating strong spectral features that reveal the physical conditions near the core. Despite their brilliance, the central regions fueling the quasar remain incredibly compact. The energy output depends on the rate at which matter falls inward, and this process can vary over time. Observations of quasars at different distances show how these energetic objects were more common in the early universe, reflecting a period when galaxies were rapidly growing and feeding their central black holes. Their immense power makes them visible across great cosmic distances. Astrobiologists study planetary atmospheres to search for chemical hints of life. To understand whether a distant world might support living systems, researchers examine the gases surrounding it with extraordinary care. When starlight passes through a planet's atmosphere during an orbit, the light carries subtle imprints created by the molecules it encounters. Sensitive instruments can separate this light into its component colors and reveal the presence of substances that may indicate biological activity. Oxygen, methane, and other reactive gases are especially interesting because they should vanish quickly unless something replenishes them. On Earth, living organisms maintain many of these gases through constant interaction with the environment. Astrobiologists combine atmospheric models, laboratory experiments, and observations across many wavelengths to determine whether unusual chemical mixtures could arise from natural processes alone, or if they might require something more dynamic. Their work demands caution because planets can produce surprising chemistry without life. Even so, each newly analyzed atmosphere adds to a growing library of possibilities. This expanding knowledge helps refine the search for planets that might host stable climates, liquid water, and long-lasting cycles that could support biology in forms familiar or unfamiliar. The surfaces of some moons are constantly reshaped by cryovolcanic eruptions. These moons contain interiors that remain warm enough to keep certain materials melted beneath their icy crusts. Instead of molten rock, their hidden reservoirs contain mixtures of water, ammonia, nitrogen, or other volatile substances that remain liquid at low temperatures. Pressure builds as these subsurface oceans and chambers shift and churn. When pathways open through cracks or weak points in the ice, pressurized material escapes in plumes that rise into space or cascade across the surface. Over time, these eruptions create smooth plains, ridges, and mottled textures that replace older terrain. The resurfacing process can hide impact craters and erase geological features that would otherwise preserve a long history. Observing these ever-changing landscapes teaches scientists how internal heat, tidal forces, and complex chemistry maintain activity in worlds far from their stars. The presence of liquid environments beneath the surface also raises profound questions about what might exist in these protected, energy-rich habitats. Gravitational lensing can magnify galaxies so distant that they would otherwise be invisible. As light travels across the cosmos, it moves through regions shaped by the distribution of mass. When a massive object lies along the line of sight between the observer and something far beyond, the curvature of space around that mass alters the path of passing photons. The effect can stretch, brighten, or multiply the appearance of the background galaxy. Instead of a single faint smudge, the observer may see arcs or rings that trace the bending of the light. This magnification allows astronomers to study structures that formed when the universe was young, revealing details about star formation, dust content, and the assembly of early galaxies. By studying the way a distant object's light becomes warped, astronomers can map the mass hidden within the lensing structure, including dark matter that gives off no light at all. Every lensing event acts like a natural telescope shaped by gravity itself, granting us glimpses of regions far too remote to observe directly. Young stars, especially those born in dense stellar nurseries, can flicker with surprising irregularity as drifting dust clouds cross our line of sight. In these birthplaces of suns, gas and dust are still plentiful. Many newborn stars are wrapped in swirling disks of leftover material, future planets, moons, and smaller worlds in the making. When clumps within these disks drift between the star and the observer, they can momentarily dim or distort the starlight. The resulting fluctuations may follow no obvious pattern because the dust distribution is constantly shifting under the influence of winds, magnetic fields, and gravitational forces. Some stars dim slowly and brighten quickly, while others show a chaotic sequence of changes. These patterns offer clues about the structure and behavior of the disks surrounding them. By studying the flickering, scientists can detect rings, gaps, warps, and regions where material accumulates. The variations also help identify potential planets forming within the disks, as their gravitational effects shape the dust. These early changes reveal the dynamic environment in which solar systems take their first steps toward maturity. Some galaxies grow by steadily consuming smaller companions. Galaxies do not always evolve in isolation. In crowded cosmic neighborhoods, large systems frequently encounter smaller ones. Gravity pulls them together slowly, causing the smaller galaxy to lose stars and gas as it spirals inward. Streams of material stretch out behind it, leaving luminous trails that mark the path of the cosmic meal. These mergers can trigger bursts of star formation as gas clouds collide and compress. Over long periods, the larger galaxy incorporates the stars of its companion, adding to its halo and inner regions. The chemical signatures of these absorbed stars differ slightly from those already present, allowing astronomers to trace the history of past mergers. This process of gradual growth plays a major role in shaping the structure of galaxies and helps explain why many exhibit complex layers, extended halos, and subtle variations in stellar populations. Each consumed companion becomes part of a larger whole, its identity preserved only in faint remnants. The atmospheres of some exoplanets glow faintly as they heat up in starlight. When a planet orbits close to its star, intense radiation warms its atmosphere to temperatures far higher than anything found on Earth. The excited molecules and atoms remit energy in the form of a delicate glow that can be detected at infrared or visible wavelengths. This emission reveals details about the gases present, their temperatures, and the dynamics of the atmosphere. In some cases, the glow shifts across the surface as winds redistribute heat from the day side to the night side. Certain planets display chemical reactions triggered by ultraviolet light, producing compounds that contribute additional brightness. By observing these faint emissions during different phases of the orbit, scientists reconstruct weather patterns, thermal gradients, and atmospheric circulation on worlds that remain unresolved as single points of light. The soft radiance that surrounds these planets offers a window into environments shaped by intense stellar energy. Planetary nebulae mark the final breaths of medium-sized stars. When stars similar in mass to the Sun reach the ends of their lifetimes, they shed their outer layers through slow winds and gradual pulsations. As the layers drift outward, the hot core left behind illuminates them with ultraviolet light. The gas responds by glowing in vivid colors that trace the composition and density of the expanding shell.
These shapes can become rings, ovals, or intricate patterns depending on the star's rotation, magnetic fields, or interactions with a companion. The nebula expands over time, gradually thinning until it fades into the background of interstellar space. The exposed core cools and becomes a compact remnant that will shine faintly for billions of years. Planetary nebulae provide valuable insight into how stars recycle material back into the galaxy, enriching future generations of stars and planets with heavier elements. Each one represents a transition from active stellar life to a quiet, final stage.
Supermassive black holes can regulate star formation across entire galaxies. At the centers of many galaxies, enormous black holes gather material into swirling disks. When the inflow becomes vigorous, the region near the core releases tremendous energy that travels outward through jets, winds, and radiation. These outflows heat surrounding gas and can push it away from the central regions. If the gas becomes too warm or too diffuse, it cannot collapse to form new stars. In this way, the central black hole influences the pace of growth across the entire galaxy. Galaxies with very active centers often show reduced star formation in their inner regions, while those with quiet centers may continue forming stars at a steady rate. This connection reveals a delicate balance between feeding the central black hole and allowing the galaxy to build new stellar populations. Understanding this relationship helps explain why galaxies differ in appearance, behavior, and long-term evolution. Some stars orbit the galactic center on paths tilted far above the Milky Way's disk. Most stars travel within the thin disk of our galaxy, but many follow orbits that rise high above or sweep far below it. These tilted, looping paths often trace back to ancient encounters, mergers with smaller galaxies, gravitational nudges from massive objects, or disruptions that occurred billions of years ago. As these stars move through their inclined routes, they give astronomers a rare three-dimensional view of the Milky Way's true shape. By studying their motions, researchers can map how mass is distributed throughout the galaxy, including the dark matter that cannot be seen directly. Some of these high-flying stars may even be the lingering survivors of dwarf galaxies long ago absorbed into the Milky Way, carrying chemical fingerprints unlike those of stars in the disk. Their unusual trajectories reveal the Milky Way's dynamic past, showing how a galaxy that looks calm today was once shaped by countless interactions and quiet collisions. Shock waves from supernova can trigger new waves of star formation. When a massive star explodes, the expanding blast pushes into surrounding molecular clouds. The shock compresses the gas and dust, increasing the density in regions that were previously too diffused to collapse. If the compression reaches a critical threshold, gravity takes over and the cloud begins to contract. New stars begin forming in the wake of the explosion, turning destruction into creation. This process helps renew regions of the galaxy and contributes to the cycling of material between generations of stars. By observing these triggered sites, scientists can follow the chain of events linking the death of one star to the birth of many others. The timing, shapes, and locations of these new clusters provide clues about how the shock wave traveled and how far its influence extended. These interactions illustrate the interconnectedness of cosmic processes, where the end of one stellar life becomes the spark for countless new beginnings. Some binary stars are so close that one pulls material off the surface of the other. In these remarkable systems, the two stars orbit each other at such short distances that their gravitational fields overlap in a delicate but powerful balance. As one star expands during its evolution, its surface can swell beyond the region where its own gravity remains dominant. When this happens, gas from the outer layers drifts toward the companion, forming a flowing bridge of material suspended between them. The receiving star often gathers the falling gas into a spiraling disk that grows hotter and denser as more material arrives. This transfer can dramatically alter both stars. The donor becomes stripped and reveals deeper layers that would normally stay hidden, while the companion grows in mass and luminosity. Sudden bursts of brightness can occur when the accreted gas heats rapidly or undergoes explosive reactions. These complex interactions help scientists understand how close companionship can reshape the lives of stars in ways that solitary stars never experience. Cosmic dust grains can contain crystalline structures forged in dying stars. These tiny particles travel through interstellar space, carrying the signatures of the environments where they formed. In the outer layers of aging stars, gas cools and condenses into solid grains as the star sheds material into its surroundings. Under the right conditions, atoms align themselves into orderly, repeating patterns that create crystals with unique chemical fingerprints. Supernova blasts and powerful stellar winds then scatter these grains across the galaxy, mixing them into clouds that will eventually form new stars and planets. When scientists analyze the light reflected or absorbed by dust, they detect subtle features that reveal the presence of these crystalline structures. Some grains are older than the solar system itself, making them relics of long-vanished stars. Their composition helps trace the cycle of material from one generation of stars to the next, showing how the universe continuously recycles the building blocks of planets and possibly even the ingredients for bye. Life stellar nurseries can form intricate networks of filaments filled with newborn suns. Within dense clouds of gas and dust, gravity gathers material into long strands that weave through the darkness like luminous threads. These filaments act as natural highways for matter to flow into regions where stars are beginning to form. As gas accumulates, knots develop along the filaments, each one gradually growing hotter and denser. Eventually, these knots collapse and ignite as young stars surrounded by swirling disks of leftover material. The filaments themselves may twist and bend under the influence of magnetic fields and turbulent motion, creating a tapestry of shapes that changes slowly over time. Observations at multiple wavelengths reveal how material moves through these networks and how different temperatures highlight distinct structures. These nurseries provide a view of the earliest stages of stellar development, showing how interconnected processes create entire clusters rather than isolated stars. Each glowing thread marks a pathway through which the galaxy continues to renew itself. Some planets develop thick atmospheres of hydrogen that dwarf their rocky cores. These enormous envelopes form when a young planet grows rapidly enough to capture light gases before the surrounding disk disperses. Hydrogen and helium flow toward the growing world and accumulate in quantities far exceeding the mass of the rocky material beneath. Over time, the atmosphere becomes a vast layer extending high above the core, blending continuously from dense lower regions into the thin outer edges. Temperatures and pressures inside this envelope can reach extreme levels, producing exotic forms of chemistry not found in smaller planets. Winds move through the atmosphere at tremendous speeds, carrying heat from one region to another and creating dynamic weather patterns that may span the entire planet. Even though the rocky core remains hidden from view, the atmosphere reveals much about the planet's history and environment. It preserves clues about the early stages of formation, helping researchers understand how planets grow and why some accumulate far more gas than others. The chemical fingerprints hidden within starlight can reveal the makeup of distant worlds.
When a planet drifts across the face of its star, some of the starlight passes through the planet's atmosphere before reaching us. Atoms and molecules within that atmosphere absorb very specific colors, imprinting faint but unmistakable patterns onto the spectrum. By studying these delicate signatures with highly sensitive instruments, scientists can identify the gases enveloping a far-off world, clues that may point to its climate, its weather, or even the geological processes shaping its surface. Remarkably, this method works even for planets we cannot see directly, opening the door to studying worlds smaller, cooler, and more subtle than ever before. As data accumulate, comparisons between different planets reveal trends in atmospheric chemistry that reflect formation history and environmental conditions. These fingerprints provide a method for examining worlds across the galaxy, using nothing more than the light they allow to pass through. This approach represents one of the most powerful tools for studying distant atmospheres without sending probes or missions to the worlds themselves. Relics of ancient galaxies remain scattered throughout the Milky Way. Long ago, smaller galaxies drifted close enough to the Milky Way for gravity to seize them. Instead of surviving intact, many were slowly torn apart as they spiraled inward. Their stars stretched into elongated streams that wrap around the galaxy like faint trails of stardust. These remnants remain visible as thin ribbons of light that trace the orbits of the long-consumed systems. Each stream carries a distinct chemical signature that differs from the stars born within the Milky Way, allowing astronomers to identify their origins. By mapping their paths, researchers reconstruct the merger events that shaped our galaxy over billions of years. Some relics appear as faint clusters still holding together, while others have dispersed into the broader halo. Together, they form a historical record preserved in starlight, revealing how the Milky Way grew by gradually absorbing its smaller neighbors. Some stars are surrounded by dusty disks left over from planet formation. After planets form within swirling disks of gas and debris, leftover material often remains in orbit around the star. Collisions between smaller bodies continually grind fragments into fine dust that spreads across the system. This dust absorbs starlight and remits it at longer wavelengths, creating a signature that can be detected with specialized telescopes. The structure of these disks varies depending on the presence of planets, which can carve gaps, shepherd rings, or scatter material into new configurations. Observing the distribution and temperature of the dust reveals the architecture of the system and helps identify regions where planets might still be forming. Over time, radiation pressure and collisions gradually remove the material. But some disks persist for hundreds of millions of years. These dusty rings act as archives of early planetary history, offering clues about the processes that shape the worlds orbiting the central star. Intergalactic gas can stretch in narrow filaments that connect distant clusters. Across the universe, matter is not evenly distributed. Instead, it collects into vast structures that form a cosmic web of clusters, nodes, and connecting strands. These filaments consist of diffuse gas, enriched with elements forged in earlier generations of stars. Though extremely faint, they span enormous distances and help channel material into growing galaxies. Observations reveal that these filaments guide the motion of galaxies and influence how clusters evolve. As gravity pulls matter along the strands, interactions between gas and dark matter shape the growth of large-scale structures. Studying these filaments requires sensitive instruments that can detect subtle signals from hot or ionized gas. Their existence confirms theoretical models of cosmic evolution and demonstrates how the universe organizes itself on the largest scales. Through them, galaxies receive the raw material needed to form new stars and continue expanding their stellar populations.
Cosmic magnetic fields can influence the motion of charged particles across huge distances. These fields arise from the motion of conductive plasma within stars, galaxies, and intergalactic gas.
Once established, they create invisible pathways that guide the movement of electrons and ions. Charged particles spiral along the magnetic lines, often traveling great distances while emitting radiation that reveals their presence. The strength and orientation of these fields vary from place to place, shaping the behavior of cosmic rays and affecting the structure of nebula and jets. In regions with complex magnetic activity, particles can become trapped in loops or channeled into narrow beams that stretch far from their origins. Understanding these interactions helps astronomers trace the flow of energy in environments where gravity, pressure, and magnetic forces all play significant roles. The influence of magnetic fields demonstrates how even unseen forces contribute to the dynamics of the universe. Some planets orbit dead stars that emit little more than faint, ghostly light. When a star of moderate mass completes its life cycle, it sheds its outer layers and leaves behind a compact remnant that slowly cools over time. These remnants produce only a dim glow. Yet, some continue to host planets that survived the dramatic transformations of their parent stars. The faint light offers minimal warmth, creating environments far colder than those around ordinary stars. Any surviving planets may have experienced intense heating during earlier phases, followed by long periods of deep freeze as the stellar remnant faded. Some planets might orbit so closely that they experience strong tidal forces, while others drift farther out in the cold. Studying these systems reveals how planetary bodies endure extreme changes and adapt to evolving stellar conditions. The continued existence shows that planets can persist even after their stars cease shining brightly. The atmospheres of some gas giants glow in infrared wavelengths. Deep within these enormous worlds, heat rises from the interior and escapes through thick layers of gas. Much of this heat is released as infrared light that is invisible to human eyes, but detectable by specialized instruments. The glow forms because the gases in the atmosphere absorb energy and later release it as gentle radiation. This steady output can reveal the temperatures, motions, and chemical makeup of the atmosphere. Winds carry heat across the surface, shaping patterns that shift slowly over time. In some giants, storms stir the gases so deeply that warm regions rise from the interior and shine more brightly than their surroundings. Observing this faint infrared light allows scientists to study the hidden workings of planets that remain distant points in the sky. These glowing atmospheres show how energy moves through deep layers of swirling hydrogen and helium, providing a glimpse into environments that dwarf the scale of any weather system on Earth. Tidal interactions can twist the outer layers of stars into elongated shapes. When two stars circle closely around one another, their combined gravity pulls intensely on each star's outer envelope. The pull is uneven. The side facing the companion feels a stronger tug than the side turned away. Over time, this imbalance reshapes the star's outer layers, stretching them along the line that connects the two partners. Instead of forming a perfect sphere, the star becomes subtly elongated. As the stars continue their orbit, the distortion shifts, causing small variations in brightness that reveal the stretching. In some systems, the effect becomes powerful enough to alter the star's rotation and even influence how energy circulates within its interior. The twisted shape may also alter how the star sheds material or how it exchanges gas with its companion. These interactions demonstrate how gravity can sculpt stars just as it shapes planets and galaxies, leaving behind visible signatures that reveal the forces at work. Some galaxies host enormous cavities. The past explosions cleared out vast regions of gas. Within certain galaxies, observations reveal huge hollowed-out areas that appear strangely empty compared to their surroundings. These cavities are thought to form when powerful events release enough energy to push gas outward. Exploding stars, energetic outflows from a central black hole, or bursts of intense star formation can all send shock waves racing through the galactic environment. As these shock waves expand, they sweep away gas and dust, leaving behind large bubbles that remain visible long after the original event has faded. The size and shape of each cavity record the history of the forces that created it. Over time, the bubbles may stretch, fragment, or refill as new material drifts inward.
Studying these features reveals how galaxies regulate their supply of gas and how energetic events influence future star formation. Each cavity represents a moment of dramatic change that reshaped its host galaxy from within. Interstellar clouds can freeze molecules onto dust grains in icy layers. In the coldest regions of space, temperatures fall so low that gases behave in unusual ways. Molecules drifting through these dark clouds can become trapped on the surfaces of dust particles. Once attached, they form thin, icy coatings that build up layer by layer over long periods. These frozen layers often contain water, carbon dioxide, methane, and other compounds that remain solid in frigid conditions. As cosmic rays and faint ultraviolet light pass through the cloud, they trigger slow chemical reactions within the ice. These reactions create more complex molecules that enrich the cloud with material that may later participate in the birth of stars and planets. When the cloud eventually collapses, the heat from forming stars evaporates the ice and releases its chemical inventory into the surrounding gas. These icy grains act as tiny storage sites that preserve the earliest stages of chemical evolution in the galaxy. Stellar mass black holes can form when massive stars collapse. A star many times larger than the Sun spends its life fusing heavy elements in its core until the reactions can no longer support its weight. When the outward pressure fails, gravity pulls the core inward with overwhelming force. The collapse proceeds so quickly that the core becomes an object of extraordinary density. If nothing can stop the contraction, the core turns into a black hole with a mass similar to that of the original star, but compressed into a much smaller volume. The outer layers may blast outward in a dramatic explosion, while the black hole remains behind as a silent remnant. Although it emits no light of its own, its presence becomes visible through its effect on surrounding matter. Gas spirals toward it, heating up and producing radiation that can be detected from across the galaxy. These remnants show how the death of a single massive star can produce one of the most extreme objects in the universe. The surfaces of neutron stars contain matter packed at astonishing densities. After certain stars explode, their cores collapse into compact spheres composed mostly of neutrons, crowded together more tightly than any material found on Earth. The surface appears solid, yet the matter within it is unlike anything in ordinary experience. At the topmost layer, atoms are squeezed into a state where electrons have combined with protons, leaving a crust of neutron-rich material. Deeper within, the density becomes so extreme that the properties of matter remain a subject of active research. The gravity at the surface is so intense that even a small irregularity could weigh countless tons. When these stars rotate or shift, stresses can build in the crust until sudden adjustments release bursts of energy detected as short flashes of radiation. By studying these signals, scientists learn more about the behavior of matter
under conditions impossible to reproduce on Earth. Neutron stars offer a unique laboratory for probing the fundamental nature of the universe. Some exoplanets orbit in chaotic systems where gravitational pools constantly shift their paths. In certain star systems, multiple planets move so closely that their mutual influences never settle into a stable pattern. Each orbit produces subtle tugs that accumulate over time, altering the shape and tilt of the paths each planet follows. The result is a dynamic environment where predictions become challenging even for advanced models. Some planets may drift slowly inward or outward, while others may change their orbital shapes in cycles that play out over long periods. The interactions can become so strong that one planet may eventually be flung into a new region of the system, or even ejected entirely. Observations of these chaotic systems reveal just how varied planetary architectures can be. They show that not all systems resemble the orderly layout seen in our solar neighborhood. Instead, the galaxy contains environments where gravity produces an ever-shifting dance that never fully repeats itself. Jets from young stars can carve long channels through surrounding gas. As a young star gathers material from its surrounding disk, some of the infalling gas becomes channeled by magnetic fields and expelled from the poles of the star at high speed. These narrow streams of material shoot outward in opposite directions, carving their way through the surrounding cloud. Wherever the jets collide with gas and dust, they compress and heat the material, creating soft, glowing regions that trace the path of the outflow. Over long stretches of time, the jets sweep aside enormous amounts of gas, opening elongated cavities that reach far from the forming star. As the young star rotates, or as conditions shift within its disk, the flow of the jet can change. These variations appear as knots, ripples, and bright pockets along the channels. By studying these patterns, scientists learn how newborn stars shed excess spin and gradually clear the dense environments from which they were born. The jets reveal both the power of early stellar growth and the complex interactions between newborn stars and the clouds that created them. Ultra-faint dwarf galaxies contain few stars, yet significant dark matter. These tiny galaxies orbit larger systems and appear as faint smudges that require careful observation to detect. Despite containing only a modest population of visible stars, they display motions that indicate far more mass than the stars alone can explain. This hidden mass is attributed to dark matter, which exerts gravity without emitting light. The abundance of dark matter helps the dwarf galaxy maintain its structure, even though its visible components are sparse. By studying the motions of the stars within these faint systems, astronomers gain valuable insight into the distribution and behavior of dark matter on small scales. These galaxies also preserve ancient populations of stars that formed early in cosmic history, offering a glimpse into conditions that prevailed long before the Milky Way took its present shape. Their faintness and simplicity make them vital tools for understanding both dark matter and the early universe. Star formation can stall when intense radiation evaporates surrounding gas. In regions where massive stars ignite, their powerful light floods the environment with heat. This radiation strikes nearby clouds and causes molecules to break apart and drift away. As the gas heats and expands, it becomes too diffuse to collapse under its own gravity. Without this collapse, the process of forming new stars slows or may even stop entirely. The influence extends through large areas, shaping where future stars can appear. Over time, the balance between heating and cooling determines whether a cloud continues to grow dense regions or becomes a largely inactive zone.
Observations of these environments reveal complex interactions between forming stars and the material that surrounds them. The struggle between radiation and gravity plays a major role in controlling the pace of star birth across galaxies. Some planets contain seas of liquid hydrocarbons instead of water. On certain frigid worlds far from their stars, temperatures fall so low that substances familiar on Earth as gases can condense into flowing liquids. Methane and ethane, which drift invisibly through our own atmosphere, become dense enough to pull into lakes and seas. These bodies of liquid spread across broad basins, carved over millions of years by rainfall that consists not of water, but of hydrocarbon droplets. The surrounding landscape may feature channels etched by rivers that carry these liquids toward larger basins, forming coastlines shaped by exotic weather cycles. Clouds of hydrocarbons gather in the sky, release storms, and refill the lakes in repeating patterns. The chemistry in these environments is rich and complex. Because carbon-based molecules behave differently under such extreme cold, researchers believe that reactions occurring at these low temperatures could create compounds not easily formed in warmer climates. These alien seas reveal that worlds can host active climates even when sunlight is faint and water is locked away as ice. Gamma-ray bursts can unleash colossal amounts of energy in a single moment. These astonishing events occur when certain stars reach the final stages of their evolution and collapse into compact remnants, or when two dense stellar corpses merge. The resulting explosion releases a concentrated flash of high-energy radiation that sweeps across the cosmos with extraordinary brightness. For a brief period, the burst outshines entire galaxies, even though the source may be no larger than a stellar core. The radiation travels outward along narrow paths, and if one of those paths happens to align with Earth, astronomers detect a brilliant flare that lasts from fractions of a second to several minutes. The afterglow continues for days or even weeks as the expanding shockwave interacts with surrounding material. These bursts provide insight into the most extreme physical conditions known, including intense magnetic fields and rapid particle acceleration. Observing them helps scientists understand how heavy elements disperse across galaxies and how violent events shape the evolving cosmos. Some asteroid families share a common origin in ancient collisions. Long ago, campless, rocky bodies moved through the early solar system on intersecting paths. When two sizable asteroids collided, the impact shattered them into numerous fragments that scattered into new orbits. Over time, these fragments continued to travel around the Sun, gradually spreading into clusters that maintain similar compositions and trajectories. By studying the colors, reflectivity, and motions of these bodies, scientists can group asteroids into families that reveal the nature of their long-vanished parent objects. These families preserve information about the conditions that shaped the early solar system and the types of materials present during planet formation. The study of these related fragments helps researchers trace the timeline of ancient impacts and understand how collisional processes influenced the distribution of material that eventually became moons, planets-C, and comets. Even today, these families continue to evolve as gravitational interactions nudge their members into new paths. Planetary magnetic fields can trap charged particles in giant glowing belts. When a planet possesses a strong magnetic field, the field extends outward into space and forms an invisible structure capable of guiding charged particles. Solar wind and cosmic rays often supply these particles, which become captured and spiral along magnetic lines. As the particles collide with atmospheric molecules, or interact with the magnetic field itself, they release energy in the form of faint light that can encircle the planet in broad, tidal regions. These belts can shift and brighten when bursts of stellar activity send waves of additional charged particles into the system. The behavior of the trapped particles reveals details about the strength and shape of the magnetic field. Studying these belts helps scientists understand how magnetic shielding influences planetary habitability, because strong fields can protect worlds from harsh radiation. The glowing regions demonstrate how magnetic forces create dynamic structures that surround planets and influence their long-term evolution. Relativistic effects near black holes can distort the passage of time. As an object approaches a region of intense gravitational pull, the fabric of space-time stretches in ways that affect how time flows. Observers far from the black hole see the approaching object slow gradually, as if its motion becomes frozen near the boundary, where escape becomes impossible. Meanwhile, for the object itself, time continues. Normally, even though external events appear to speed up dramatically, the differing perceptions arise because gravity influences not only spatial trajectories, but also the rate at which time progresses. These distortions grow stronger the closer matter falls toward the black hole. Instruments that listen to the signals from spiraling gas detect subtle shifts, changes in frequency and timing, that confirm the slowing of time in these extreme environments. Understanding these effects is essential for exploring how black holes interact with their surroundings and how gravity behaves when pushed to its limits. They remind us that time is not a rigid stage on which the universe plays out, but a flexible, responsive dimension shaped by mass, energy, and motion itself. Some galaxies rotate around enormous concentrations of dark matter so diffuse and invisible that they can only be traced through their pull. Their stars, gas, and dust move far too quickly to be held together by visible matter alone. Instead, a hidden halo of unseen mass embraces the galaxy, providing the gravity needed to keep it from flying apart. This hidden mass forms a halo that surrounds the visible disk and extends far beyond its outer edges. The stars orbit within this halo, following paths shaped by the distribution of dark matter rather than solely by the luminous material. Observations of rotation curves reveal that the gravitational pull remains strong even where visible matter becomes scarce. By mapping these motions, astronomers infer the structure and density of the dark matter that dominates the galaxy's mass. Although dark matter does not emit or absorb light, its effects on the dynamics of galaxies provide crucial clues about the composition of the universe and the processes that govern cosmic evolution. The atmospheres of some exoplanets contain clouds made of vaporized minerals. In extreme environments close to their stars, temperatures soar high enough to vaporize rock. Minerals that remain solid on Earth turn into gases and rise into the upper atmosphere, where they condense into clouds of tiny droplets or crystals. These clouds form intricate layers that vary with altitude, temperature, and chemical composition. As the planet rotates, winds carry the mineral-rich vapors across the sky, producing variations in brightness that shift with the orbital phase. Observing these changes allows scientists to study the mineral content of the atmosphere and model the conditions on the planet's day and night sides. Such exotic clouds demonstrate the extraordinary diversity that exists in planetary atmospheres across the galaxy. They show that even familiar elements can behave in surprising ways under different temperatures and pressures, creating skies unlike anything found within our solar system. Starquakes can rattle the surfaces of neutron stars. These compact stellar remnants have crusts that behave like rigid surfaces resting at oceans of extraordinarily dense matter. As the star rotates or undergoes internal changes, stresses accumulate in the crust. When the stress becomes overwhelming, the crust shifts suddenly and releases energy in a seismic event that resembles an earthquake. These starquakes send vibrations through the entire object and can produce flashes of high-energy radiation detectable across great distances. Some quakes also alter the rotation of the neutron star slightly, creating measurable changes in the timing of its pulses. By studying these events, scientists gain insight into the internal structure of neutron stars and the behavior of matter under extreme pressure. The quakes reveal how the dense surface responds to ongoing changes within the star, offering clues about phenomena that cannot be replicated on Earth. Some stars are so massive that they fuse elements up to iron in their cores. During their lifetimes, these enormous stars burn through their fuel at astonishing rates, progressing rapidly from hydrogen to helium, then to heavier elements. As the temperature and pressure in the core rise, fusion reactions produce carbon, oxygen, neon, and other intermediate elements. Eventually, the core becomes hot enough to fuse silicon into iron. At this stage, energy production reaches a halt because fusing iron does not release energy. Without a fresh supply of outward pressure, the core collapses, leading to a catastrophic explosion that scatters the star's material into surrounding space. The heavy elements created during this final fusion cycle contribute to the chemical richness of the galaxy. By observing these massive stars at different phases of their evolution, scientists learn how they shape cosmic environments and provide the raw material for planets and future generations of stars. Distant planetary systems can contain icy bodies far beyond their giant planets. Far from the warmth of the central star, temperatures fall to levels where water, methane, carbon dioxide, and other volatile substances freeze into solid form. These remote regions often host populations of icy objects that orbit quietly and rarely interact with the inner system. Their surfaces remain unchanged for long periods, preserving clues about the earliest stages of planetary formation. When scientists detect these distant bodies, they analyze their orbits to learn how the system evolved and whether giant planets migrated during its youth. The distribution of icy material helps reveal how disks of gas and dust developed around young stars. By comparing remote objects in various systems, astronomers gain insight into how common such outer reservoirs are, and how they influence the potential for comets, moons, and other icy wanderers to form. These distant bodies enrich our understanding of planetary diversity across the galaxy. The faint glow between galaxies contains the afterglow of ancient stars. In the vast spaces separating galaxy clusters, a delicate light lingers that is almost impossible to detect without sensitive instruments. This glow arises from stars that were stripped from their original galaxies during past collisions and gravitational interactions. As galaxies passed one another or merged, some stars were flung into intergalactic space, where they continued shining in isolation. Over time, many of these stars dimmed, aged, and eventually faded, yet their combined light forms a soft radiance that fills the darkness between clusters. This glow holds clues about the history of galactic interactions, because the number and brightness of the stray stars reflect how often galaxies collided, merged, or cannibalized their neighbors. By analyzing this faint emission, astronomers reconstruct events that took place over billions of years. The light becomes a quiet record of cosmic history, revealing the long and intricate journeys of stars that now drift far from any galaxy. Some comets release jets of dust and gas as they approach their stars. These icy wanderers spend most of their lives in remote regions where temperatures remain extremely low. As a comet drifts inward toward the gentle warmth of its star, sunlight begins to seep through its frozen outer layers. The ices trapped within start to warm and vaporize, building quiet pressure beneath the crust until it finally escapes, bursting outward through tiny cracks and fragile seams. These vents release streams of dust, vapor, and shimmering ice grains, forming the soft, glowing coma that envelops the comet's dark nucleus. The jets can sway, pulse, or drift as the comet turns, each plume responding to how sunlight strikes its uneven surface. The material they carry becomes the beginning of the comet's luminous tails, those long, delicate streams that always point away from the star's light. By watching these shifting outflows, scientists learn what lies hidden inside: the chemistry of ancient ices, the structure of the crust, and the way primordial material responds to warmth after billions of years in darkness. For a brief moment, these ancient ingredients return to visibility before fading once again into the cold. Galactic winds can blow gas out of galaxies and quench star formation.
In regions where many massive stars form and die in rapid succession, powerful outflows of energy arise from their combined activity. Supernova explosions, intense radiation, and fierce stellar winds push surrounding gas outward with tremendous force. This material can escape the gravitational pull of the galaxy, reducing the supply of cool, dense gas needed to form new stars. Over time, these winds may reshape the structure of the galaxy, creating large cavities and sweeping channels that mark the pathways of the escaping material. The loss of gas slows the birth of new stars and may eventually bring star formation to a near halt. Observing these winds helps scientists understand why some galaxies remain active while others fade into quieter phases. The presence of such winds demonstrates how feedback from stars influences the long-term evolution of galaxies and regulates the balance between creation and destruction within them. Some stars wander the galaxy at high speeds after gravitational encounters. During close interactions with clusters, binary companions, or spiral arms, stars can receive sudden boosts of velocity that send them racing across the Milky Way. These encounters occur when gravity from multiple sources acts in just the right way to accelerate the star. In extreme situations, the star may be propelled so strongly that it escapes the galaxy entirely and becomes a solitary traveler in intergalactic space. Even when the speed is not high enough for escape, the altered trajectory can carry the star far from its birthplace. By tracing their paths backward, astronomers identify the crowded or unstable regions where these stars originated. Their unusual motions reveal details about the gravitational landscape of the galaxy and the interactions that shape stellar populations. Each wandering star becomes a messenger, carrying information about the dynamic forces that govern motion within the Milky Way. The surfaces of some exoplanets may be covered in oceans of molten rock. On worlds that orbit very close to their stars, temperatures rise high enough to melt the upper layers of the crust. The result is a shifting sea of liquid rock that glows with intense heat. These magma oceans can extend across entire hemispheres or wrap around the planet, depending on rotation and heat distribution. Gases released from the molten surface form atmospheres filled with vaporized minerals that condense into glowing clouds. Winds carry these vapors to cooler regions, where they solidify and fall back as mineral-rich rain. The boundary between molten and solid terrain shifts continually as the planet rotates, creating dramatic temperature contrasts
between the scorching day side and the cooler night side. Studying the light emitted by these planets allows scientists to infer the composition and temperature of their molten surfaces. These extreme environments demonstrate how closely a planet can approach its star before its geology is transformed into a dynamic ocean of rock. Supernova remnants can contain swirling knots of highly enriched gas. After a massive star explodes, the expelled material expands into the surrounding space in a complex mixture of shock waves and glowing debris. Within this expanding cloud, clumps of heavy elements form as the gas cools and interacts with itself. These knots contain elements forged in the star's core or produced during the explosion, making them pockets of material that differ significantly from the surrounding gas. As the remnant grows, its filaments twist into intricately shaped structures, each glowing at specific wavelengths that reveal its elemental composition. Scientists study these knots to understand how supernovae distribute heavy elements throughout galaxies. These materials eventually become part of new stars, planets, and even the building blocks of life. The presence of these enriched regions shows how the death of one star contributes to the chemical diversity of future generations. Some galaxies harbor enormous amounts of cold molecular hydrogen. This invisible gas forms the raw material for star formation, yet it emits very little detectable radiation at typical interstellar temperatures. Instead, astronomers identify it by observing the faint emissions from molecules that accompany it, such as carbon monoxide. In certain galaxies, especially those undergoing rapid growth, vast reservoirs of cold hydrogen remain hidden until detected through careful surveys. These reservoirs can extend across large regions and fuel waves of star formation that last millions of years. The presence or absence of this cold gas determines whether a galaxy will continue forming stars or enter a quieter stage. By mapping where the gas resides, scientists gain insight into the processes that drive galactic evolution, from mergers to internal dynamics. This hidden component of galaxies plays a central role in shaping their behavior across cosmic time. Stellar collisions can create unusually massive and luminous stars. In crowded environments, such as the cores of dense clusters, stars may pass so close to one another that their outer layers merge. If the collision is gentle enough, the stars combine into a single object with far greater mass than either possessed previously. The new star becomes hotter and brighter because its increased mass allows it to fuse elements at a more rapid rate. These collision-born stars stand out among their neighbors due to their intense blue light and surprising youth compared to the surrounding population. Observing them provides insight into the dynamic interactions that occur in dense stellar environments. Their existence demonstrates that not all stars form from simple gravitational collapse. Some emerge from the violent but creative encounters that take place in the crowded realms of clusters. Some planets experience extreme temperature swings between day and night. Planets orbiting close to their stars may rotate slowly or become tidally locked so that one side always faces the star while the other remains in perpetual darkness. The day side heats to scorching levels, while the night side cools to frigid temperatures. Between the two hemispheres lies a region of dramatic gradients where intense winds attempt to redistribute heat. The atmosphere circulates rapidly, carrying warm material toward the night side and returning cooler gases toward the day side. These patterns create complex climates that vary with altitude, cloud formation, and atmospheric composition. Observing these temperature contrasts allows researchers to infer how energy moves through the atmosphere and how stable the climate might be over time. The extreme differences between day and night conditions reveal the diversity of environmental conditions that planets can host, even within the same system. The outer edges of some galaxies contain stars that barely orbit at escape speed. Far from the bright central regions, the gravitational pull of the galaxy weakens, and the stars in these remote outskirts travel more slowly than those closer in. Yet the presence of dark matter creates a gravitational field strong enough to keep these distant stars bound, even at the far edges where the galaxy's pull grows faint. Some stars wander along enormous, slow-moving orbits, drifting so far from the center that they travel through regions where the Milky Way's grip almost slips away entirely. Their quiet, looping paths help astronomers trace the true extent of the galaxy's dark matter halo, an invisible sphere far larger than the bright disk we see in the night sky. By studying the speeds and distribution of these remote stars, scientists uncover how galaxies grow, how mass gathers, and how unseen matter sculpts the structure of the cosmos. These outermost regions are a frontier where the visible world of stars meets the silent domain of the unseen, revealing the vast reach of galactic gravity. Some black holes emit soft X-rays as matter spirals inward. Although black holes themselves produce no light, the material swirling around them forms a brilliant display that radiates across many wavelengths. As gas from a nearby star or cloud drifts toward the black hole, it accelerates and compresses into a thin disk heated to millions of degrees. The inner regions glow intensely, often releasing a gentle but detectable form of X-rays known as soft X-rays. These emissions help scientists study conditions close to the point where gravity becomes overwhelming. The pattern and strength of the radiation reveal how quickly matter is falling inward and how the disk is structured. Variations in brightness can indicate turbulence, magnetic disturbances, or changes in the supply of nearby gas. Observing these soft X-rays provides rare insight into environments that lie just outside the boundary where escape is impossible. They offer a window into the final moments of material that is about to vanish from view forever. Complex organic molecules can form in cold, dark nebulae within the deepest reaches of interstellar clouds where starlight barely penetrates. Temperatures drop low enough for exotic chemistry to unfold slowly over long periods. Dust grains coated with thin layers of ice serve as tiny laboratories where atoms gather and react. Cosmic rays and faint ultraviolet light can penetrate these shadows, just enough to trigger interactions between molecules trapped in the icy coatings. Over time, these reactions produce intricate organic structures that include chains, rings, and branching arrangements of carbon compounds. When the nebula begins to collapse and warm, the ice evaporates and releases these newly forged molecules into the surrounding gas. Their presence enriches the material that will eventually form stars and planets. Detecting these compounds in cold clouds provides evidence that the basic ingredients needed for biological chemistry can arise long before any planets exist. These dark regions reveal that life's building blocks may begin assembling in the quietest corners of space. Some exoplanet atmospheres expand into huge, puffy envelopes. In extreme environments where a planet orbits close to a bright star, the intense radiation heats the outer atmosphere until it swells dramatically. The expanded gas becomes so diffuse that it extends far from the planet's surface, forming an inflated envelope shaped by stellar winds and gravitational pull. These envelopes can grow larger than the planet itself by many times, creating structures that resemble drifting clouds rather than compact atmospheres. The gases may escape slowly into space, creating long trails of material that follow the planet along its orbit. Observing the absorption of starlight during transits reveals how these extended atmospheres differ from more compact ones. The size, composition, and temperature of the envelopes provide clues about the planet's history and how strongly it interacts with its star. These swollen atmospheres showcase the dramatic effects of heating in close orbit conditions and expand our understanding of how planetary atmospheres respond to extreme radiation. The earliest galaxies formed when the universe was still young and chaotic.
In the first few 100 million years after the birth of the cosmos, matter clumped together under gravity to create the seeds of future galaxies. These early structures were small, irregular, and filled with rapidly forming stars whose intense radiation reshaped their surroundings. Collisions between young galaxies occurred frequently, mixing gas and triggering bursts of star formation that burn through material at astonishing rates. The universe at this time lacked many of the heavy elements produced by later generations of stars, so the earliest galaxies contained pristine gas that behaved differently from the enriched clouds found today. Observations of distant galaxies allow astronomers to peer back through time and study these early stages. The light from ancient stars carries the imprint of a universe that was constantly shifting as new structures emerged and old ones merged. Understanding these chaotic beginnings reveals how the familiar galaxies of the modern cosmos came to be. Some stars form in metal-poor environments that challenge current models. In certain regions, the gas available for star formation contains very few elements heavier than helium. These environments resemble the conditions of the early universe when heavy elements were scarce. Stars that form in such metal-poor clouds behave differently because the lack of metals affects cooling processes, internal structure, and the rate of nuclear reactions. These stars often shine with unusual colors or exhibit chemical signatures that stand out from typical stellar populations. Their existence helps scientists test theories of how stars evolve when the ingredients available at birth differ from those found in enriched regions. Observing these rare stars reveals how the universe produced its first generations and how subsequent waves of star formation gradually increased the abundance of heavy elements. They provide a glimpse into an earlier epoch when the cosmic landscape was far simpler and more pristine. Galactic bars can funnel gas towards central star-forming regions. Many galaxies display an elongated structure of stars and dust stretching across their centers. This bar acts as a gravitational bridge, guiding gas from the outer disk toward the galaxy's inner regions. As the material streams inward along this elongated structure, it collects in dense pockets where pressure rises high enough to ignite bursts of star formation. These newborn clusters glow brilliantly, lighting up the clouds around them like small constellations contained within the galaxy itself. Over time, the bar may strengthen, weaken, or subtly shift as the galaxy's internal motions evolve. Its influence extends throughout the entire system, shaping rotation patterns, steering the flow of gas, and helping to sculpt the central bulge. By observing barred galaxies, astronomers learn how internal structures choreograph the movement of matter and guide the slow unfolding of stellar history. The steady flow of gas along the bar shows how galaxies renew themselves over millions of years, maintaining quiet cycles of activity that gradually transform their form and brightness. Some planets orbit multiple stars in wide, looping trajectories. In stellar systems containing two or more stars, planets can follow paths that circle the entire group rather than just one member. These wide orbits must balance the combined gravitational influence of the stars, creating intricate trajectories that shift as the stars move relative to one another. Depending on the arrangement, the planet may experience cycles of intense illumination, followed by periods of dimmer light as it moves through the changing geometry. The climate on such planets could vary dramatically because the combined starlight can fluctuate over long timescales.
Observing these systems reveals the resilience of planetary formation in complex environments. Despite the shifting gravitational landscape, many planets settle into stable orbits that persist for billions of years. Their existence shows that planetary systems can thrive even in places where multiple suns dance around one another in repeating patterns. Cosmic shock fronts can energize particles to extreme velocities. When fast-moving matter collides with slower gas or dust, it creates a boundary where the sudden compression produces a surge of heat and radiation. These shock fronts occur in supernova remnants, galactic winds, and regions where jets from compact objects encounter surrounding material. As particles cross these fronts, they bounce back and forth between regions of differing magnetic fields, gaining energy with each pass. Over time, some particles achieve velocities that approach the speed of light. These energetic particles contribute to cosmic rays that travel across interstellar and intergalactic space. By studying the emission from shock fronts, scientists learn how energy is transferred in extreme environments and how high-energy particles influence their surroundings. These processes help shape the distribution of gas and contribute to the evolution of galaxies. Some galaxies shine brightly in radio wavelengths due to energetic processes. In many galaxies, certain regions produce strong emissions, detectable in the radio part of the spectrum. These emissions often arise from electrons moving at high speeds through magnetic fields. The motion creates a kind of radiation that reveals the presence of energetic activity near jets, supernova remnants, or dense star-forming regions. In some galaxies, a central black hole accelerates particles that generate radio waves spanning thousands of light years. Radio observations allow astronomers to peer through dust that obscures visible light, revealing structures hidden deep within the galaxy. By mapping radio emissions, researchers uncover patterns of motion, regions of past explosions, and the activity of jets that extend far beyond the visible disk. These bright radio signatures provide a deeper understanding of the forces shaping galaxies. Dusty tori around active galactic nuclei obscure their central engines. At the hearts of certain galaxies, supermassive black holes feed on surrounding material and release enormous energy. However, thick rings of dust and gas encircle many of these central engines. These tori block the direct view of the inner regions when observed from certain angles. The dust absorbs high-energy radiation and remits it at longer wavelengths, creating a signature that reveals the presence of the hidden core. The shape and thickness of the torus influence how the galaxy appears across different wavelengths. Studying these obscuring structures helps scientists understand how central black holes grow, how they interact with their surroundings, and why some active galaxies appear bright while others seem faint. The dusty tori act as gateways that regulate how much of the central energy escapes into the galaxy. Some planets may host subsurface lakes trapped between layers of rock and ice. On certain cold worlds, sunlight provides too little warmth to sustain liquid water at the surface. Yet, deep beneath the frozen crust, heat from the planet's interior can slowly melt pockets of ice. These pockets expand into hidden lakes, sealed beneath layers of rock, sediment, and ice that act as insulating blankets. The boundaries between these layers create pressure that keeps the water from freezing, even when temperatures above remain far below the freezing point. Minerals within the surrounding rock dissolve into the liquid, creating a chemically rich environment. Tidal forces from nearby moons or a parent planet may stir the interior slightly, helping maintain the delicate balance between freezing and melting. These lakes can persist for extremely long periods, because the layers above shield them from radiation and turbulent surface conditions. Scientists believe such environments could support complex chemistry and perhaps even simple biological processes. These subsurface reservoirs reveal that liquid water, a key ingredient for life, may be far more widespread in the universe than surface observations alone would suggest. Intergalactic stars drift far from any galaxy after tidal stripping. When galaxies interact or merge, powerful gravitational tides stretch and pull their outer regions. Stars that formed on the outskirts of these systems may be flung free during the encounter. Once separated, they drift through intergalactic space without the familiarity of a nearby stellar neighborhood. These isolated travelers continue shining as they move through a realm where matter is sparse and darkness dominates. Their motions trace the long-forgotten collisions that scattered them. By observing their speeds and paths, astronomers uncover clues about past events that shaped entire clusters of galaxies. These stars also provide information about the chemical makeup of the galaxies that once held them. Though solitary, they contribute faint light that blends into the soft, intergalactic glow. Each star becomes a relic of a dramatic event, carrying a quiet but enduring record of forces strong enough to unbind it from its original home. Some stellar winds are so powerful that they carve out vast bubbles in space. Massive stars release intense streams of charged particles that race outward at tremendous speeds. These stellar winds sweep through the surrounding interstellar medium, pushing aside gas and dust and expanding waves. Over time, the winds create enormous hollow regions that can span dozens of light years. The edges of these bubbles glow where compressed material becomes heated by radiation from the star. Inside the cavity, the gas becomes thin and hot, shaped by the ongoing flow of the wind. As the star evolves, the bubble can grow, deform, or split into multiple chambers, depending on the surrounding environment. Observing these structures helps scientists gain insight into how stars influence the material around them, and how energy from massive stars regulates star formation in their neighborhoods. Each bubble becomes a monument to a star's power, preserving the history of its interactions with the interstellar landscape. Proton stars accrete material through swirling disks of gas and dust. In the earliest stages of stellar formation, gravity draws matter inward toward a growing central object. Instead of falling straight in, the material forms a flattened disk that circles the protar. Within this disk, collisions and interactions gradually remove some of the material's rotational energy, allowing gas and dust to spiral inward. As the protar gains mass, pressure and temperature rise in its core, pushing it steadily toward the moment of ignition. Meanwhile, the disk continues to evolve, with some portions gathering into clumps that may eventually become planets or smaller bodies. Jets may emerge from the poles of the protar, carrying away excess angular momentum and shaping the surrounding cloud. Observations of these disks reveal how the earliest stages of star and planet formation proceed. The smooth, inward flow of material marks one of the most important steps in the birth of stars throughout the galaxy. Some galaxies experience bursts of star formation that consume gas rapidly. During certain periods of the galaxy's evolution, conditions may align in a way that triggers rapid and widespread creation of new stars. Collisions with smaller galaxies, inflows of fresh gas, or internal instabilities can compress material into dense pockets where star formation ignites at an accelerated pace. These starburst regions shine brightly as thousands of young stars heat and illuminate surrounding clouds. The newly formed stars release strong winds and radiation that eventually disrupt the very clouds that created them. As these forces push gas outward or heat it so much that it cannot collapse, the starburst slows and eventually fades. This cycle can transform the appearance of a galaxy in relatively short cosmic times. Studying these bursts reveals how galaxies grow, change, and regulate their own star-forming activity over time. High-energy photons from young stars ionize nearby nebula. Newborn stars, especially massive ones, emit intense streams of ultraviolet light that pour into the surrounding clouds of hydrogen-rich gas. When these high-energy photons strike the atoms in the cloud, they knock electrons free and create regions of ionized gas. These ionized zones glow with vivid colors that trace the movement of radiation through the cloud. The photons continue to drive changes in the nebula, carving shapes, opening cavities, and generating pressure that reshapes the surrounding material. Observing these glowing regions provides insight into how star formation progresses. As time passes, the young stars clear away much of the cloud, but the nebula remains as a record of the early relationship between newborn stars and the material that formed them. These bright regions serve as signposts of stellar youth across the galaxy. Some moons contain complex geology shaped by internal heating. Beneath the surface of certain moons, heat generated by tidal forces, radioactive decay, or leftover energy from formation can drive geological activity. This internal warmth may melt pockets of rock or maintain layers of soft material that shift and flow over time. Cracks, ridges, and varied terrains appear on the surface as the interior expands, contracts, or circulates slowly. In some cases, plumes of gas or icy particles rise from fissures, offering glimpses into the chemical makeup of the hidden regions below. The patterns of fractures and smooth plains reveal long histories of tectonic and volcanic processes. By studying these features, scientists gain insight into how moons change over time and how their internal conditions differ from those of larger planets. These active interiors reveal that even small worlds can sustain dynamic, energetic environments powered by processes unfolding deep beneath their surfaces. Black hole accretion flares can shift dramatically in just moments. As matter spirals toward a black hole, the infalling stream is rarely smooth. Gas can gather into clumps, twist into spirals, or collide within the accretion disk, producing sudden rises or dips in brightness. When these dense pockets of material fall inward or interact with powerful magnetic fields, they release bursts of energy that appear as rapid, flickering flares, brief but telling signatures of the extreme physics at play. These changes occur over minutes, hours, or days, depending on the size of the black hole and the structure of the disk. Observing the timing and intensity of these flares offers insight into conditions near the event horizon, including turbulence, temperature gradients, and the behavior of magnetic fields. The variability provides clues about how matter organizes itself under extreme gravity. Each flare becomes a fleeting signal from the very edge of one of the most enigmatic objects in the universe. Some exoplanets orbit so far out that their year lasts centuries. In the outskirts of certain planetary systems, faint and distant worlds move along immense orbits that take them far from their stars. Because the gravitational pull is weak at such distances, these planets travel slowly and complete their orbits over timescales far longer than a human lifetime. Conditions on these worlds remain cold and dark, with only faint starlight reaching their surfaces or atmospheres. The long cycles of seasons and orbital motion create environments unlike those found closer to the star. Studying these distant planets reveals how large planetary systems organize themselves and how outer regions evolve. These wandering giants help scientists understand how planets migrate, how disks of gas and dust disperse, and how the architecture of a system reflects its earliest stages of formation.
Relics of ancient star clusters drift through the galaxy as faint, luminous traces. Some clusters that once held together tightly have gradually lost their stars to gravitational forces within the Milky Way. Over time, their members spread out along extended paths that follow the cluster's original orbit. These streams of stars remain faint but detectable, with precise measurements of motion and chemical composition. Each star in the stream carries the same elemental signature forged in the cluster's birth environment. By mapping these stellar trails, astronomers reconstruct the shapes and lifetimes of clusters that no longer exist as unified groups.
These drifting remnants reveal how the galaxy's gravitational field stretches and disperses smaller structures. They serve as quiet reminders of ancient gatherings of stars that once shone brightly, but have since been pulled apart by the steady motion of the galactic tides. Drift now into the quiet part of the night, where the rush of thoughts begins to loosen, and the edges of wakefulness grow soft. You have traveled through distant galaxies and ancient starlight, through worlds made of ice and fire, and through cosmic landscapes that unfolded gently around you. Let all of that sink into the background like a fading tide. There is nothing you need to remember, and nothing you need to hold on to. The universe will continue its slow and patient motion without any effort at all from you. Feel the breath settle in your chest, as if it were rising and falling with some distant cosmic rhythm. Imagine the stars thinning into a soft glow behind your eyelids. You are safe. You are still. You are floating in a place where the night welcomes you fully. Each inhale gathers the last traces of the day. Each exhale lets them drift away. If you are still awake, you can always return to another video on this channel. There will be more journeys waiting for you whenever you want to wander again. Soft stews, gentle science, quiet wonders, all here to ease you toward rest whenever you choose. For now, though, allow yourself to let go. Let your thoughts move more slowly. Let your body rest a little deeper. Feel your mind become lighter and quieter, like a small moon settling into a peaceful orbit. There is nothing you must do. There is no destination you need to reach, only the calm that gathers around you, patient and warm. Settle into that calm now. Let it carry you the rest of the way. Good night.